Amplifiers. Good morning students. Today the topic of discussion is microwave amplifiers and I am Shivani Sharma from GPC Khunimachra, Mohali, and I am here to discuss the microwave amplifiers which is covered in the subject of microwave and radar. Today we will discuss the introduction to the microwaves, then limitations of the conventional devices at higher frequency, then introduction to microwave tubes, then we will discuss the principle of operation of microwave amplifiers, types of microwave amplifiers, in which we will discuss Klystron amplifier, reflex klystron, travelling wave tube amplifier and magnetron. First of all, introduction to microwaves. Microwaves are electromagnetic waves whose frequencies range from about 300 megahertz to 300 gigahertz, and the wavelengths in the air ranging from 100 centimeter to 1 mm. Means when we are talking about microwave, these waves are very high frequency waves. The range of these microwave electromagnetic waves are ranging from megahertz to gigahertz. And if we talk about in terms of wavelength, the wavelength in air range is varying from 100 centimeter to 1 mm. So, the word microwave means very short wave when we are talking about in terms of wavelength, which is the shortest wavelength region of the radio spectrum and a part of electromagnetic spectrum. Means microwaves, if we see in the terms of frequency, this is very high frequency waves because we are talking about in terms of gigahertz. But when we are saying in terms of wavelength, it just varies from 100 centimeter to 1 mm. So, which is a very short wave. That is why these waves are called as microwaves. Now, we will discuss the various properties of microwave. Microwave is an electromagnetic radiation of short wavelength. Then they can reflect by conducting surfaces just like optical waves, since they travel in straight line. Then microwave currents flows through a thin out layer of an ordinary cable, and microwaves are easily attenuated within short distances. They are not reflected by ionosphere. So, these are some properties of microwaves. Means first, they are electromagnetic radiations of very short wavelength, just having 100 centimeter to 1 mm range. After that, they can be reflected through any conducting surfaces just like optical waves. Then the microwave currents can flow through the thin outer layer of a ordinary cable, and microwaves are easily attenuated within short distance and they are not reflected by ionosphere. Now, what are the advantages and limitations of microwaves? In terms of advantages or merits, first point is increased bandwidth availability. Means microwaves have large bandwidths as compared to the common bandwidth like short waves, ultra high frequency waves. So, when we compare the microwaves with these short waves or ultra high frequency waves, their bandwidths are very large. Then if we see, for example, microwaves are extending from lambda 1 centimeter to lambda 10 centimeter, that is 30,000 megahertz to 3000 megahertz. So, this region has a bandwidth of 27,000 megahertz. Second property is improved directive property. The first point is increased bandwidth, because we are talking about microwaves are ranging in gigahertz. So, bandwidth is very large. So, as the bandwidth is very large, the transmission capacity, we can say it is also very large. The capacity of the system is also very large. Second is improved directive properties. The second advantage of microwaves is their ability to use high gain directive antennas. Any EM wave, electromagnetic wave, can be focused in a specified direction. Means improved directive properties, it is related with the use of directional antenna. Means with microwaves we can use directional antenna, and by using the directional antenna we have directive properties, we have higher gain. Then the third is fading effect and reliability. Fading effect due to the variation in the transmission medium is more effective at lower frequency. Due to the line of sight propagation and high frequency, there is less fading effect, and hence microwave communication is more reliable. When we are talking about fading effect is the variation in the transmission medium, and it is very effective when we are talking about low frequency. But at higher frequency signals, as in the case of microwaves, due to the line of sight propagation, the fading effect is very less, hence the communication system, microwave communication, is proved to be more reliable. Then next is power requirement. The transmitter and receiver power requirements are pretty low at microwave frequency compared to that of shortwave band. Means the power requirement is also very low when we are talking about microwaves. And the last is transparency property of microwaves. Microwave frequency band is ranging from 300 megahertz to 10 gigahertz and are capable of freely propagating through the atmosphere, and the presence of such a transparent window in a microwave band facilitates the study of microwave radiation from the sun and stars in the radio astronomical research of space. Transparency property of microwaves is related with that it can freely propagate through the atmosphere. So, this property is transparency property of the microwaves. Now, the various applications of microwaves. Microwaves have a wide range of application in modern technology, which are as first is in the field of telecommunication, the intercontinental telephone and TV, space communication. Space communication relates to earth to space and space to earth, and telemetry communication link for railways. So, in all these communication links or space communication, the microwaves are used nowadays. Then second is radars. In radars, the application is to detect the aircraft, track and guide supersonic missiles, observe and track weather patterns, then air traffic control, burglar alarms, garage door openers, police speed detectors, etc. So, in the field of radars, the microwaves are used. Now, we will discuss the limitations of conventional devices when they are operated on high frequency. Means that why we are not using conventional device on microwaves. The reason is that there are certain limitations, and these limitations are inter-electrode capacitance, lead inductance effect, transit time effect, gain bandwidth limitation, effect of RF losses, then effect due to radiation losses. So, these are some limitations of conventional device when they are operated on high frequency signals. So, first is inter-electrode capacitance effect. Like in a vacuum tube, at low or medium radio frequencies produce capacitive reactance that are so large that no serious effect upon tube operations are noticeable. However, as the frequency increases, the reactances becomes very small enough to materially affect the performance of the circuit. Means just like our conventional device is a vacuum tube, when vacuum tube is operating on low or medium frequencies, the capacitive reactance is so large there is no effect on the circuit operation. But when as the frequency is increasing, this reactance is becoming very small and they have effect on the performance of the performance of a circuit. For example, a 1 microfarad capacitance has reactance of 159,000 ohms at 1 megahertz. And if this capacitor was the inter-electrode capacitance between grid and the plate of a tube, and the RF voltage between these electrode was 500 volts, then 3.15 milliamperes of the current would flow through the inter-electrode capacitance. So, the current flow in this small amount would not seriously affect the performance of the circuit. This is the inter-electrode capacitance effect. The inter-electrode capacitance effect comes into the picture like we have a capacitance when we have two conducting plates and we are having some dielectric medium in between them. So, if we see this circuit diagram, we have three conducting electrodes, and among these three conducting electrodes there is a dielectric medium like vacuum which is acting as a dielectric medium. So, this is acting as a capacitance and this capacitance is called inter-electrode capacitance like CPG and CPK and CGK. These three capacitances are inter-electrode capacitance. So, on the other hand, at a frequency of 100 megahertz, the reactance would decrease to approximately 1590 ohms, and with the same voltage applied, current would increase to 315 milliamperes. So, here we can see as the frequency is increasing and this capacitive reactance is decreasing, the effect of current flowing through the circuit will increase when we are applying the same voltages. So, a good point is to remember that higher the frequency or larger the inter-electrode capacitance, then higher will be the current flowing through this capacitance. And as the frequency of input signal increases, the effective grid to cathode impedance of the tube decreases because of a decrease in the reactance of inter-electrode capacitance. And if the signal frequency is 100 megahertz or greater than that, then the reactance of grid to cathode capacitance is so small that much of the signal is short circuited within the tube. Since the inter-electrode capacitance are effectively in parallel with the tuned circuits, so they also affect the frequency at which the tuned circuits are resonate. Now, the second limitation is lead inductance effect. Another frequency limiting factor is lead inductance effect of tubes. Since the lead inductances within a tubes are effectively in parallel with inter-electrode capacitance, the net effect is to raise the frequency limit. However, the inductance of the cathode leads is common to both grid and the plate circuits. This provides a path for degenerative feedback which reduces overall circuit efficiency. So, here we can see as this lead inductance effect comes into the picture, the overall circuit efficiency decreases. Now, the next effect is transit time effect. Transit time is time required for the electrons to travel from cathode to anode. While some small amount of transit time is required for electrons to travel from cathode to the anode plate. The time is insignificant at low frequencies, means this transit time is nearly to negligible and it is very small when we are talking about low frequencies, but in fact the transit time is so insignificant at low frequency, that is, it is generally not considered to be a hindering factor in the performance of the circuit. However, at higher frequencies the transit time becomes appreciable portion of a signal cycle, and then it becomes to hinder the performance of the circuit. Means when we are talking about at higher frequency, this transit time effect becomes so large that it begins to hinder the performance of the circuit. Then transit time, initially this current is in phase with the grid voltage. However, since transit time is an appreciable part of a cycle, the current arriving at the plate now lags the grid signal voltage. As a result, the power output of the tube decreases and the plate power dissipation increases. So, another loss of power occurs because of electrostatic induction. So, the electrons forming the plate current also electrostatically induce potentials in the grid as they move past it, and this electrostatic induction in the grid causes currents of positive charges to move back and forth in the grid structure. So, this back and forth action is similar to the action of hole current in the semiconductor. Now, we will discuss the microwave tube principle. The efficiency of conventional tubes is largely independent of frequency up to certain limit, and when this frequency increases beyond the limit, several factors combine to rapidly decrease the tube efficiency. So, tubes that are efficient in microwave range usually operate on the principle of velocity modulation, a concept that avoids the problem encountered in the conventional tubes. So, velocity modulation is more easily understood. The factors that limit the frequency range of a conventional tube are thoroughly understood. So, what is the principle of velocity modulation? We will discuss now. The microwave tube was developed when the use of frequency spectrum went beyond 1000 megahertz and into the microwave range. The microwave tube uses transit time effect in the conversion of DC power to radio frequency power, and the interchange of power is accomplished by using principle of electron velocity modulation and low loss resonant cavities in the microwave tube. Basically, in the operation of microwave tube, the limitations which we have discussed earlier, like transit time effect, we use that transit time effect to change DC power into RF power signal, and this interchange of power is accomplished by using the principle of electron velocity modulation. As electron has mass and thus exhibit kinetic energy when in motion, the amount of kinetic energy in an electron is directly proportional to its velocity, and that is, the higher the velocity, higher is the energy level. So, the basic concept of electron energy level is being directly related to the electron velocity, which is the key principle of the electron energy transfer and the amplification in the microwave tubes. Means in microwave tubes, how we achieve the amplification, that is the amount of energy level is proportional to the velocity of the electron. If the velocity of electron is very high, then we say that higher is the energy level. So, an electron can be accelerated or deaccelerated by electrostatic field. So, this is how we achieve the amplification in microwave tubes. See, in this diagram, we have one positively charged body and negatively charged body. Electrons are moving from negative to positive charged body. As electron is moving in an electrostatic field, the direction of travel shown by this heavy arrow is against the electrostatic lines of force, which are from positive to negative, and the negatively charged electron will be attracted to the positively charged body and will increase in velocity. As its velocity increases, the energy level of electron will also increases. So, an electron travelling in the opposite direction to the electrostatic lines of force will absorb energy and increase in velocity, means it will accelerate, and an electron travelling in the same direction as the electrostatic lines of force will deaccelerate and it will give out the energy to the field. So, the negatively charged body will repel the electron and cause it to decrease in the velocity. When the velocity is reduced, the energy level is also reduced and energy lost by the electron is gained by the electrostatic field. So, the operation of velocity modulated tube depends on a change in the velocity of electrons passing through its electrostatic field. A change in the electron velocity causes the tube to produce bunches of the electron, and these bunches are separated by the spaces which there are relatively few electrons. Means by varying the velocity of electrons, we are forming the bunches of the electrons, and the variation in the velocity of beam of electrons caused by alternating speeding up and slowing down the electrons in the beam. So, this variation is usually caused by a voltage signal that is applied between the grids through which these electron beam must pass through. So, what we are doing in the microwave tubes, we are forming the bunches by varying the velocity of the electrons, and after that we are accelerating these electrons, and after some time by deaccelerating these electrons we are taking out the energy in the RF field. So, this is the diagram. Here at the one end we have cathode, we have accelerator grid and we have a buncher grid. The function of this buncher grid is to form the bunches, and after forming the bunches, these bunches are moving further towards the anode side. So, electrons emitted from cathode are attracted towards a positive accelerated grid, but all but a few of electrons pass through the grid and forming a beam, and the electron beam then passes through a pair of closely spaced grids called buncher grids. Each grid is connected to one side of tuned circuit, and the buncher grids are then dashed lines which are at the center of the cavity and which are the same DC potential as the accelerator. So, the alternating voltage which exists across the resonant circuit causes velocity of electrons leaving the buncher grids to differ from the velocity of electrons arriving at the buncher grids. So, the main in microwave amplifiers, the main motivation and objective is that these amplifiers are used to increase the voltage, current or power of a signal and are used in most of the transmitters and receivers. and the principle is simple, that is velocity modulation. Now, the Klystron tube, which is the first microwave amplifier. A Klystron tube, it is a specialized linear beam vacuum tube. Klystrons are used as amplifier at microwaves and radio frequencies to produce both low power reference signals for super heterodyne radar receivers and to produce high power carrier waves for applications such as radars and microwave relay transmitters and driving force for modern particle accelerators. So, these are the some applications of the Klystron tube. The basic is two cavity Klystrons are velocity modulated tubes that are used in radar and communication equipments as an oscillators and as a amplifiers, and Klystrons make use of transit time effect by varying the velocity of an electron. So, a power amplified tube is used to amplify the weak microwave energy signals to high power levels for radar transmitters. So, a Klystron is characterized by high power, large size, high stability, high gain and high operating voltage device. A Klystron is something referred to as a linear beam tube because the direction of electric field that accelerates the electron beam coincides with the axis of magnetic field, whereas in contrast the magnetron, which are also acting as amplifiers, they are as a cross field devices. So, Klystrons provide a coherent transmitted signal appropriate for Doppler radar and pulse compression applications. So, the history of these Klystron tubes, the two brothers like Russell and Sigurd Varian of Stanford University are the inventors of the Klystron tube. Their prototype was completed in August 1937 and upon publication in 1939, news of Klystron immediately influenced by the work of US and UK researchers working on radar equipment. So, this is the constructional view of the Klystron tube, in which on the one side we have cathode and another side anode is acting as a collector. In between these cathode and collector we have two cavities. First cavity is buncher cavity and second cavity is catcher cavity, and the space between these buncher and catcher cavity is called drift space. So, the function of buncher cavity is to form the bunches, and at the catcher cavity we are getting out the amplified signal. So, here we can see at the buncher cavity at the lower end we have microwave input, and at the catcher cavity we have microwave output, which is the amplified signal. And now we will discuss how this amplification is done in the Klystron tube. This is the another view of Klystron tube. If here the same thing is, one is cathode, another end is anode, which is acting as a collector, and in between them we have two cavities, buncher cavity and catcher cavity. In the buncher cavity we are giving the input signal, at the catcher cavity we are getting out the output signal, and in between them we have a drift space. So, the working of Klystron tube: strong electrostatic fields are necessary in the operation of Klystron tube. This is necessary because interaction of signal and the electron beam take place in a very short distance. When the tube is energized, cathode emits the electron, which are focused into beam by a low positive voltage on control grid. Then the beam is then accelerated by a very high positive DC potential, and after accelerating it will passing through the buncher grids, The buncher grades are connected to a cavity resonator which superimposes an AC potential on the DC voltage. AC potential signal which we are taking as an RF input. So, the AC potentials are produced by oscillation within the cavity and begin spontaneously. When the tube is energized, the initial oscillations are caused